Okay, so you guys have already done a little bit with vectors in physics, so some of what we do is probably going to overlap what you've done. We might look at things a little differently. We look at it more from a mathematical perspective and a lot of right triangle trig. But we'll go through it, and then if there's differences with what you've done in physics, let me know, and maybe we can kind of make it seem like the same thing. So if there's a way you already know how to do it, that might work for this too. Right, so first of all, a vector is used to measure two things at the same time. Does anybody know from physics what the two things a vector measures are?
Magnitude and direction.
Yeah, it measures the magnitude and the direction. So what would be an example of something that would have a magnitude to it and a direction? Yeah?
Velocity.
Yep, velocity. So a certain speed, but you also have to know a certain direction. And with velocity, we'll do an example, and we'll use like a compass heading. That'll be our direction. So we'll say like a plane is flying northeast, like a 45-degree angle, and it'll hit wind. And we'll figure out how far off course the plane is going to be blown. Okay, so we'll do an example like that. What else besides velocity? Yeah?
Acceleration.
Acceleration? All right, so yeah, acceleration has a direction to it, and it has a numerical component as well, which how fast you're accelerating. Yeah?
Force.
And force, that's an example. So you might be pushing on an object, but you also might push on it at a certain angle. Yeah.
Displacement.
Displacement. That's all kinds of examples. Anything that has a direction to it and a magnitude. Okay, something like temperature. That wouldn't be a vector. Okay, a temperature is just a number. There's no direction really associated with temperature. Now, if you were to study heat flow, maybe you could talk about a vector with that, like heat transfer, moving from one place to another, like in a metal rod. There might be a direction, the way the heat travels in the rod, from like the hot area to the cold area. Right? And there might be a speed at which that happens. So maybe using calculus, you could figure out if somebody holds an aluminum rod at one end, or holding it would be a bad idea, putting a thermometer on it, and you start heating it, how long would it take before the other end reaches 200 degrees? Right? That would depend on what the rod's made of. Depends on how hot of a flame you're using to heat it. Depends on how long the rod is, if it's a foot long or is it 20 feet long. But eventually the heat will transfer through the rod. Okay? That gets a little more complicated. We won't be getting into stuff like that. Okay, what we are going to do is represent a lot visually. Okay, at least in the first lesson. And then we'll start to get away from the visual stuff and do more just arithmetic and calculations on paper. Okay, but the idea when we draw a vector, we'll represent it as an arrow. Okay? The length of the arrow will represent the magnitude. And the direction you point it in, that will be the direction. All right, so earlier I brought up a website that had airplanes kind of traveling in different directions. And you could think of all those airplanes as vectors. All right, so if we take a look at that. So if you look at all these different planes, they all have some same direction, but different directions they're traveling in. And they also have different speeds they're traveling at. Right? So you think of them as vectors. But what makes it a little bit complicated is you've got to think of it 3D. So I think there's two planes here. There's like one right there, one right there. Even though it looks like these planes are really close, it looks like there's massive collisions about to happen, they could be at different altitudes. Okay, one could be at 30,000 feet, one could be at 10,000 feet. So they have to think about that too. But basically it's the job of somebody at Logan, okay, air traffic controller, to coordinate all the traffic coming into and out of Logan Airport. So using computers and people, they try to make sure that there's always a certain amount of space between all these planes. So if something does go wrong, there's still room for these planes to adjust if they need to fly around a storm or whatever happens. But thinking about them as vectors kind of simplifies the process for a computer. It's just a bunch of arrows moving at different speeds. And the computers make sure that they don't intersect. Right, so any question on that idea? So it's an application for vectors. All right, and as we start to zoom out a little bit, we'll start to see really the massive amount of like coordination
Holy crap.
that you need to do. So there's that JFK down there. There's quite a few planes down there, yeah. And all these planes, they look. There's a lot of planes. Okay, they look extremely close, but really it could be like miles and miles and miles between all these planes. It's just there's so many of them when you zoom out.
Then you go up to Canada and there's hardly anything going on.
Yeah, it's not as much. Yeah, in fact, you can look at if you look at an outline of all the flight paths of planes in the United States, you can pretty much see the outline of the whole country just by looking at the flight paths. You can see because the planes pretty much fly on every border, every possible spot you could fly in the country, except I didn't notice it in the Southwest, kind of like near northern Arizona, maybe parts of Utah, really remote. I didn't see any planes flying over that section, but pretty much everywhere else in the country, planes fly over, almost everywhere. Okay, so tons of planes. All right, so when we draw a vector using an arrow, the arrow has 2 points on it. Okay, it has an initial point and a terminal point. Okay, in geometry, this would be very similar to a shape that you start. Well, a basic shape that you study. It's a ray. It's got a starting point and a terminal point. If you switch the initial and terminal point, it does make a difference. So we got to make sure we have it pointing the way we want. Okay, in our book or that packet I gave you, you might see vectors written a couple different ways. Generally, they use a bold letter. Okay, to represent a vector. If you look on page 335 in the packet, you'll see it right there. Sometimes on paper, bold letters are hard for us to do, so you can put a letter with an arrow over it. This arrow doesn't indicate direction at all when it's above a letter. All it's indicating is that the M is a vector. Doesn't mean it's pointing to the right. It's just that M is a vector. So, any question on the different notations? So in this lesson, I think I mostly use the bold letter, just like your book does. How about in physics? Do you have a certain way that you represent vectors? You use this way? You could also do 2 letters. If you did like a ray in geometry, that also tells me that it's going from P towards Q. In that case, it does tell me. Versus if I did this, that's different. This is not what I have a picture of right there. Right, so you could use that notation as well. All right, so we're going to talk about what happens when you combine vectors. We're going to do addition, subtraction. Later on in the week, or next week, we'll do multiplication. We won't do division. Division of vectors isn't really something that you do. It's not really a defined operation. First thing to make sure you understand is that when you combine 2 vectors together, you get a new vector. Right? If you think of that as a force, okay? Let's say you're pushing down on the table. Actually, straight down on the table with a certain amount of force. And then somebody else comes next to you and also pushes down on the table with a certain amount of force. Well, the result of that is an even stronger vector pushing down with an even stronger amount of force. Okay, so when you combine 2 vectors together, you get a new vector. Any question on that idea? Let's see what happens when we try to add vectors graphically. Okay. To add vectors graphically, we already kind of looked at something like this earlier in the week. Okay, you're basically going to connect arrows together. Right? I think we looked at it when we added complex numbers visually, looking at the real components and the imaginary components. Well, the idea is that you take the ending point of one vector and put it right on top of the beginning point of another vector. Right, so the terminal point of one vector, put it right on top of the initial point of the next vector. So when you do that, you can have something that looks like this. The end point and beginning point right on top of each other. And then to get your answer, okay, basically what would the vector be if we combined these two? Draw a vector from the initial point to the terminal point. Okay, so what I just drew in red, that would be the vector you'd get if you combine the two in black. And if you had more than two vectors, you just keep stacking them all together. So if you had one like this, one like that, one like that, one like that, and you wanted to know what would be the effect of combining all four of those vectors, take the beginning point, take the ending point, and connect them. What's in red represents combining all those vectors in black. Any question on that? Good. So let's try it a little more precisely. So I set up a grid. You don't need a grid to do this, unless you're trying to measure something. Okay, but we're not measuring the length yet. We're just going to combine it. All right. So it doesn't matter where you place V. You just place it somewhere on that grid. Take W. Make sure you line it up so that the beginning of W and the end of V coincide. Any question on that stuff? Right, then our last part, draw, let's see. I'll do the answer as a dotted line. Well, I thought I would. So this was V, W, and that dotted line represents V plus W. Okay, there is an arrowhead. I don't think you can see it. Maybe if I can kind of see it. You got to make sure you put the arrowhead on it so I know which way it points. Right. Questions on adding vectors visually? Okay, before we even try to add these, just look at them for a second. And I want to try to figure out what's going to happen. Any thoughts on what's going to happen here when you add these up? Taylor?
Well, they cancel each other out.
Yeah, they cancel each other out. So we're going to take the end point of one and line it up with the beginning point of another. Okay, so let's do that. Let's see what happens. Okay, now your final answer is to connect. It's kind of hard to show, but once they're on top of each other, I want to connect that to that, and that's my final answer. Well, since they're exactly the same length and they point in opposite directions, connecting them, basically I don't have a vector. What I would connect from and to is the same point. So what's my answer? Anybody know how you could write the answer? Visually, there's really nothing to draw. But what did we say earlier? When we combine vectors, you always get what? Adding two vectors together gives you your new vector. So technically, there is a vector there. Does anybody know what vector it is? It's special vector.
Are you looking for like an equation, or is there like a name for it?
No, there is a name for it.
Oh.
It's a vector with no magnitude and no direction. So we said all vectors have to have magnitude and direction, but this one's kind of an exception. Well, if these were numbers, try to think of it that way. What would you have just gotten when you combined things that were opposites? Yeah? Yeah, you would have gotten 0, the number. Well, the answer to this is 0, the vector. So it's either a bold 0 or like that. Okay, it's called the 0 vector. Right, and that's also explained on page 335. Right, so you combine two vectors that have the same magnitude but opposite directions. You get a new vector called the 0 vector. Okay, vector addition is both commutative and associative, okay, which means if we add vectors together, we can change the order we do it, and it doesn't affect the final answer. Right, to show that, let's take v plus w. Let's add them up. That's v. That's w. And add them up. Okay, so what I just got in red, that's v plus w. Now I'm going to switch it. I'm going to take w, and I'm going to add v onto the end of it. Any questions on how I just switched it? I basically went from doing this, which is v plus w, to that, which is w first, and then put v on the end. Well, look at what you get when you do that. It's the same thing. Okay, so switching the order that you add two vectors in doesn't make a difference. You still get the same answer. Okay, we can also do the associative property. That works as well. So associative property doesn't have to do with changing the order. It has to do with changing the parentheses. The order is the same on each side. ABC, ABC. We're just going to change what we add first. Okay, so in the first one, we'll do a plus b. We'll get that answer. And then we'll put c on the end of it. So there's a plus b. Add those up. Right, so we've got a plus b. Which one was b? Was b the shorter one originally? That's going to be important. Right. And now I'm going to take and add c onto the end of that. It's almost horizontal, not quite. So draw a vector from here to there. So what's in green is my final answer. Okay, that red vector just represented a plus b. Right, so this is a plus b plus c. Now let's switch it. Let's do b plus c first, and then add a onto the end of it. Right, so here's b plus c. Okay, so now we got that, b plus c. And now take and do a and put b plus c on the end of it. So there's a. The one in red is b plus c. And let's see what happens. Get the same thing. Right, so the associative property works for vectors. Any question on that? So that's more of a visual thing. You can't really write all that down in your notes, moving things around like that. But it's just a visual way to show you that associative and commutative property work for vectors. Okay, what would be the difference between those two vectors? V and negative V. Well, you could tell me what would also be the same. What's different? What's the same?
Magnitude would be the same, the direction would be different.
Yeah, the magnitude is identical. The direction is just opposite. Exactly. So we've already seen this idea earlier. If you've got two vectors that are the same, and you add them together, or two vectors, I'm sorry, that are opposites, same magnitude, different direction, the answer you get is the zero vector. Okay, the zero vector is the only vector that has no magnitude to it, and it really has no direction. It's kind of a special case. So we can use this idea right here to do subtraction. So if I asked you to do, let's say, V minus W, how do you think you would do that? We don't really have a way to do subtraction. We have a way to do addition. So how could you change this into an addition problem? Yeah?
V plus negative W?
Yeah, V plus negative W. As long as you know what negative W means, you can easily find that. Take W and reverse the direction it points, or rotate it 180 degrees, however you want to think about it. And now we can do subtraction. Right, so to subtract two vectors, take the second vector, find the opposite of it, and then add. Okay, so in physics, do you guys do a lot of it visually, or do you do more of it just looking at numbers and you don't draw arrows?
So probably more visually.
So you do draw lots of arrows and that kind of stuff? Yeah. The diagrams can be helpful, especially when you're doing like a word problem, to kind of set it up and see it. But I think once you get beyond the initial diagram, then it's helpful to just do numbers. So then you're just doing like sines, cosines, stuff like that. But yeah, diagrams definitely very helpful. All right, so I want to find V minus W. Okay, I got V. Justin, what's the first thing I have to do if I'm going to subtract W?
Really, let's get the nuts.
How can you rewrite this? Since it's a subtraction problem, we need to rewrite it.
You want to like rewrite it as addition?
We want to rewrite it as addition, yeah.
Negative W plus V. Or, no.
Don't technically you could do that because of the commutative property, but don't switch the order. I want to keep V as positive. I don't want to change V to negative. That would change my problem. Yep. V plus negative W. So technically, Justin, what you said, negative W plus V would work. But we'll keep it in that order rather than switch it. But it would work. All right, so we got V. Okay, so that's good. Now we need negative W. Well, to find negative W, I can do two things. I can reflect it horizontally and then reflect it vertically. So if you remember from geometry, that's something you can do to basically rotate 180 degrees. Okay, just like what I did. So now, I just took V, I put negative W on the end of it, and there's my answer. That's V minus W. Okay, any question on that? Okay, so as you start to do the homework tonight, there'll be a lot of problems that have graphing in them, so you will need a piece of graph paper, which I can give you if you'd like some. Okay, scalar multiplication. Okay, anybody know what that is? Scalar multiplication. Yeah?
So in physics, we learn about scalar and vector properties. So vector has magnitude and direction. Scalar only has magnitude.
All right, so a scalar, yep, is just a number. And what does it mean to scale something? Like if I said make a scale model of that house, or build me a scale model of a car or something. What's a scale?
To make something with the same like proportions but different size.
Yeah, so we can make something a different size. So with a vector, it's really, the way we're looking at it right now, it's a 2D thing. So all we can really do is change the width of the vector. That wouldn't make sense to make a thicker arrow, but longer and shorter. Okay, that would make sense. So when we multiply a vector by a number, as Marina said, just a number. That's what a scalar is. This gives us a new vector. Now, a scalar can do three things to a vector. Basically, three things. Kind of gave away a little bit of it, but anybody have an idea what's one thing that a scalar could do to a vector? Yeah?
Stretch it.
Yep, make it longer, definitely.
Make it shorter.
Could make it shorter. What else could happen? Could make it longer, could make it shorter. Think about all the kinds of numbers that you could multiply by. Yep?
It could flip it or take it, make it the opposite.
Right. What kind of number would do that?
The negative.
A negative. So if you multiply by a negative, that's going to reverse the direction of it. Now you could multiply by a negative 1/2 and do two things at the same time. Make it half as long and flip the direction. But those are the three things that a scalar can do. Lengthen, shorten, or reverse direction. Any question on those three? All right. So this is an example of what doing a scalar product would look like. 2v, okay, or 1/2 v. Okay, we didn't really explain this yet, but just using common sense, what do you think the 2 is going to do to v? Think it's going to lengthen it or shorten it? Yeah, yeah, it's going to lengthen it. Right, so the idea is if you take one copy of v, take another copy of v, and now draw your vector. What I just drew in green, that's 2v. Again, either use the bold letter or just put an arrow over it. Either way. Okay, 1/2 v. That's a little more difficult to do on the smartboard. There's no button I can press that's going to automatically take half of it. So if I was doing it on graph paper, I would measure the length of it, put a point at the midpoint, okay, between the initial and the terminal, and then draw my vector. Okay, so maybe something like that. Okay, so that's 1/2 v. Notice in both cases the direction didn't change because I didn't use a negative. Right, so this one they have you finding negative v. Okay, we've already done one like that earlier. Just take and switch the direction. That is one I could do on the smartboard just by reflecting it twice, but it's quicker to just draw it. So there's negative 1v. To get negative 1/3 v, again, that's when you got to estimate. You'd have to find the length. And then go 1/3 of the distance. Okay, just estimate it. Maybe about like that. And that's negative 1/3 v. Questions on that? All right, so sometimes what they might have you do is scale a vector and then add them. Let's just do this one. 2v plus 3w. How would I do that? Anybody explain to me? Let me start with v. I want to find 2v plus 3w. First step. Yeah.
So first step would be you want to find 2v.
Okay. So I'm going to find 2v. How could I do that? Let's say I'll make a few copies of it.
Just double it so we join them and
Yeah, just join these two together. Doesn't matter where you put your initial point. Just put it right there. Okay, so there's 2v, and now what?
then you need to find 3w.
Yeah, I need to find 3w. All right, so just make some copies of that. There's 1w. There's 2w. And 3w. Okay, so 2v, that's the positive slope going up and to the right. 3w, it's going down and to the right. And just connect it. Try to make it straight. So that's 2v plus 3w. Okay, any question on that? So you just have to scale it first and then add them. If they did subtraction, you would just have to find the opposite direction, and then you could scale that bigger or smaller if you needed to. In this case, you wouldn't. You'd just take two of the v's, flip the direction of w, don't scale it at all, and then add u on it. Okay. All right. Okay, so that symbol, when you put a vector, and you put these double bars on each side of it, you guys use that symbol in physics? No? Okay, well that symbol represents the magnitude. Okay, in other words, all I want to know is how long the vector is. Okay, that's what that symbol means. Because it's a magnitude, it's a length, it's always positive. You'd never have negative length. The direction might be pointing in a different way, but that's separate. Okay? Length doesn't matter which way the arrow is pointing. So thinking about what I just said, what would be the difference between the magnitude of v and the magnitude of negative v? Josh? There is no difference. These are exactly the same thing. Changing the direction something points doesn't change how long it is. Okay? Exactly the same magnitude. If the magnitude of a vector happens to come out to 1, okay, that's called a unit vector. We'll study unit vectors in the next lesson quite a bit more. Do you guys use the vectors I and j at all? No? I, j. How about k? If you do 3D? No? We're going to study I and j. These are unit vectors. We'll explain them in the next section. And when we start to do 3D, then we'll introduce k. Right, but that's all a unit vector is. It's a vector that's 1 unit long. Right, so to perform any kind of algebraic operations on vectors, we've got to start getting away from the visual drawing of arrows. Like, if all I need to do is add 2 vectors, it's not very convenient to have to use graph paper and connect them, right? For several reasons. One, let's say you had vectors that were huge, right? You're either going to have to scale your graph paper or use really big graph paper. You need a ruler, okay, to draw this stuff straight. So diagrams are good to kind of start out with, but very quickly from a diagram you want to just get into calculations, okay, and leave the diagram behind, especially for addition and subtraction. So this is another way to write a vector. Okay, use these brackets. How about that notation? Do you guys use that at all? to ever represent vectors?
Yeah, great.
Some people yes, some people no, some people in different physics classes maybe. I don't know. But yeah, this is almost like a coordinate, except it's got brackets. And that's important. That's the only thing that makes it different from a coordinate. If you put parentheses, it's not a vector. So basically what A and B are the horizontal and vertical components of a vector. So I have, yeah. Okay, so let me show you an example. Suppose you had the vector 2, 3. All that this means is you're going to draw a vector that has a horizontal component of 2 and a vertical component of 3. Is there a right or a wrong place to start from? If I just said to you, draw the vector that has a horizontal component of 2, vertical of 3.
You start from the origin.
Okay, you can start from the origin. If I started somewhere else, though, would it be
You
wrong?
start off like the last vector.
Yeah, what?
You start off with the last vector.
This is the only vector you're going to have. I'm going to just draw that one vector. So there's only going to be one vector in this whole picture. But what I'm getting at is it telling me exactly where I need to start?
No, it's just telling you where to go from where you start.
Right. It's just basically saying from some starting point, okay, from an initial point, how far left and right, and then how far up and down. Now, it is good to start at the origin. That's the best place to start. But in this notation, not required. Okay, so if I just said to you, draw a vector, 2, 3. You could start here, go 2 units right, and then 3 units up. Okay, that's the vector 2, 3. Okay, this is also the vector 2, 3. Put it over here. That vector goes 2 units right and 3 units up. Okay, and as Brian said, you could also start from the origin, which is the best place to start because then your initial point is 0, 0. And when you have to start doing arithmetic, 0, 0 is an easy coordinate to work with. Why put it down in quadrant 3? Now you've got to deal with negatives in your coordinates. It makes finding distances and everything that much harder because the negative some people get confused on, especially when you have minus a minus, they forget to make it plus and all that kind of stuff. All right, so again, A tells you the horizontal component, B tells you the vertical, but it doesn't tell you where to put it. Put it wherever you want. As long as it starts 2 units right and then 3 units up, that's where it ends. All right. If the vector does start at the origin, okay, if its initial point is at the origin, it's called a position vector. Okay, on that other page I had up, there was only one position vector. Everything else didn't start at the origin. Okay, and the last thing is we'll look at how could you find a position vector. Right, let's say we'll look at one of those other ones I drew. We'll look at the coordinates and see if we could figure out how we could figure out the position vector. Okay, let's do, just so we don't have to deal with too many negatives, let's do this one. We could have used any of them, but this will simplify it a little. What's the coordinates of this point right there? Make it a little bigger. What's the coordinates of that point? Josh?
5, 3.
1, 2, 3, 4, 5, 3. Yep. And the coordinates of that terminal point. About Brandon?
7, 6.
Yeah, we'll go over 2 more from that, so 7. We're already up at 3, 4, 5, 6. Now remember the original vector was 2, 3. is there any way we could take these coordinates, do something with them, and somehow get a 2 in one spot and a 3 in the other? And if you can do this, it would tell you what the position vector is.
Subtract the initial point from the terminal point.
Yeah, if you wanted to find what this vector is, I mean, yes, you could just count over 2, up 3. But if you didn't have it on a grid, all you have to do is subtract the initial points. Well, as Michael said, subtract the terminal point from the initial. Where you ended minus where you started. Not the other way around, because that'll reverse the direction. So 7 minus 5 gives me 2. 6 minus 3 gives me my 3. Right, so if you've got a vector that has initial point, call it x1, y1, terminal point, x2, y2, you basically do p2 minus p1, or x2 minus x1, and y2 minus y1. And that'll tell you what the vector is, if you're given 2 points. Right, and that's helpful to have, because then we know, okay, once we have that vector, if we wanted to start at the origin, just go left or right, however many units you get for the x2 minus x1, and then go up or down, however many units you get for y2 minus y1. Okay, putting your initial point at the origin is always a good idea. All right, so our last one, they give us 2 points, and they just want us to find the position vector. Let's start with our x component. How about Julia? What would be my x component?
5.
Yeah, it'd be 4 minus negative 1, okay, which gives us a 5. Okay, and Nick, how about my y component? Anyone help him out? How do we get that y component? Yeah, Josh? How'd you get 4? Yeah, just 6 minus 2. So there's the vector that represents those points. If they don't label which one is initial and terminal, always assume P1 is initial, P2 is terminal. All right, so the homework, again, don't forget it's in your packet. It's not in the book, so you don't need your book for this. It's 1 to 10 all, 14 to 22, just the evens, 26 to 32, also just the evens. And on 26 to 32, they ask you to do a couple different things. I just want you to find the position vector. Don't worry about the other thing they're asking you to do. We'll do that next time. Okay, and tomorrow we have our test on 8.2 through what we just did today. And I will be after school if anybody needs extra help.